Hi, so this is the second part of the Chapter 2 lecture. So I said at the end of the last video that there are three ways we're interested in representing logic relations. And the three ways, let me just write it up here, the three ways are Boolean expressions, and we'll figure out what that means shortly. The second way is, funnily enough, logic circuits. And the third way is what we have on this slide now, which are truth tables. And all three of these are useful, and they all show pretty much the same information. It's just they do it in more compact, less compact, more visual ways. So here we have three basic logic operations. The AND operation, which is written like this, which says X and Y. And we've got what a truth table does is it enumerates all the possible inputs to the function, in this case the AND function, the logical AND function, and it tells you what the output is for all possible inputs. So here, because we only have two inputs, X and Y, there are only a total of 4 possible overall inputs, and the output is only ever 1 when both X and Y are 1. So the next one is the OR operation, and this is confusing, but the OR operation is written with a plus sign. So do not confuse the plus sign with the AND operation. It is OR. And here we're interested in X or Y. Now, in English, usually X or Y is what I would call an exclusive OR. But in logic, this OR operation is called an inclusive OR. So an inclusive OR is 1 when Y is 1, is 1 when X is 1, and is 1 when both of them are 1. Right? So it's an inclusive OR. There's another thing called an exclusive OR that we'll talk about a little later. And then the third operation here is the NOT, or the complement, or the inverse operation. And sometimes this is written as it's written here with a prime symbol. I tend to use an overbar symbol when I write it. So X bar is the way I would say that, or the other one is X prime. Sometimes, if you're into programming, sometimes a way to do that is to precede it with an exclamation mark. But that's not usually used in digital logic. So when we use digital numbers, binary numbers, in computers, the computers are in the physical world. They have voltages. And one of the things we need to do when we go from the physical world into the virtual world of binary is we need to decide what voltage represents a 0 and what voltage represents a 1. And we don't want those two to overlap because we don't want to have, ooh, is that a 0 or a 1? So this is what this diagram is showing, right? It's showing that there's a transition region between the signal range for a logic 0 and the signal range for a logic 1. And different device types use different values for the numbers 0, 1, 2, 3 on this axis. These could be volts, but for a lot of the devices we're using, the signal range needs to be closer to about 5 volts for logic 1 rather than just 3 volts. Some of the newer devices run at 3.3 volts or even 2 volts, but we're using some of the older 74LS series devices, and they're about 5 volts. Right, so here's another way of showing the truth table that we had before. There's an AND gate, and there's an OR gate, and there's a NOT gate or an inverter. Right? It takes the complement. And you need to start getting familiar with how to convert between those different representations of the Boolean expressions. X and Y, X or Y, or complement of X, or X bar, or inverse of X. We won't get there for a while, but one of the things we're going to be interested in is seeing how these things work over time, right? So this plot is showing how, so this axis along here is the time axis, and it's showing how X and Y change. Excuse me. And what that means as far as how the output X and Y, X or Y, and not X. Excuse me. The devices we had before only have 2 inputs, but it's perfectly possible to have more than 2. Here's a 3-input AND and a 4-input OR. Okay. Please have a look at this video. Please read through the tutorial I'm going to get you to work through during our first class, and I'll see you